Everybody, just want to let you all know, I'm actually sending an email to the whole class right now. I've got a faculty something tomorrow that they're making us go to, and normally my office hours are from 10 to noon. I've got to push them noon to 2. And it's just for this Friday. That won't be a normal thing. Does that totally mess you up? Or okay. So I will be there, but just not until around noon. Might be earlier, but we'll see how my thing goes. So I'm sending that out right now. Do we have questions over things out of the homework yet? Okay. Give me just a second. Your quizzes are over here from last time, and the clickers are over here. Please go grab it. Close time. So I have a quiz planned for today, and I forgot to print it. So we can do it on your own sheet of paper, or why don't we do this? Let's do. I think this will be a good compromise. How about we do it where I allow you to work in groups on this quiz, but I don't answer any homework questions till after the quiz. That sound fair? Fair? Okay. So this will be a group quiz. Make sure you grab your clicker. Just take out a sheet of paper. It will be timed. Each person will have their own sheet of paper. What is that? You don't have a piece of paper?
I do, but it's going to get all...
That's okay. I'd rather have it on that than some random other piece of paper. Let's go ahead and click in for attendance. All right. Everybody in? Okay, last call for attendance. Last call. Where? Is his stuff here? Like? Yeah? All right, well, he can deal with that after he comes back. All right, so the quiz, I plan on putting this all on 2 pages, so let me just move it to 1 page. Is that the one you had a question on? Okay. All right, well, see how you do. Show me something at least. Okay. I believe these, the first one I made up, the second one is right out of the homework. Why will that not go away? There we go. Christian, just hand him back stuff. Sean. Eddie? Tien? Jennifer? Chris? Juarez? Jennifer Ferris? No? Okay, testing audio here. Just right here, please. Thank you. Has everybody turned them in? Here we go. Thank you. Everybody ready for the weekend? All right. All right, should we go through these? All right, so for this first one, you would want to first figure out what happens when you plug 3 in for x, right? So 3 squared on top is 9, 9 minus 9 is 0. And then when you plug in 3 here, 3 squared is 9, 2 times 9 is 18. Then you have here 9 again, so you're taking away 9, and then taking away another 9. So 18 minus 9 gives you 0. So you have 0 over 0. Anytime you have 0 over 0, you do what? You got to figure something out, right? And I talked about that last class, and I put something on the board, right? Today I have a handout for you. Take these and then pass them back that way. Everybody have a copy of this? All right. I do not want to get you to the point where you would want to use this on a test. Okay, I would prefer that this not be something you need, but at least for now it's something to guide you. All right, and then something you could keep in your folder. If you take Cal 2, you have this as reference. All right, this is kind of a summary of everything we're going to look at with limits. We're only addressing some of these today. Right now, on the left side of this, the column on the left is the form of the limit that you have. So what are you looking at? And then on the right, it tells you what you need to do in order to figure out that limit. Right now, we have this form, right, of 0 over 0. Very important to make a distinction here. When we plug 3 in, right, this thing is undefined. Yes? But we know that the top is headed towards 0, getting closer to 0, the closer we get to 3. The bottom is headed closer to 0, the closer we get to 3. So it's the form of the limit that we're interested in, not the fact that it's undefined at 3. Yes? The difference is key here. So if you have 0 over 0 in a limit, then you're going to use some sort of algebra or some trick. All right? So the algebra that we would use for this would be factoring, yes? So we rewrite the limit because we have not let x go to 3 yet. We factor the numerator as a difference of squares. We factor the denominator as, what, it's a trinomial, right? So we have to figure out what numbers work out here. 2x, x, what, minus 3, is it minus 3? Yes. And then plus 1, no, plus 3, yes? So the expectation, again, is that you are comfortable factoring. And now, if you do this, you are allowed to cancel any factors. So I can cancel these factors so long as I promise that x will never be 3, right? But that's what this limit means. I'm going to let x get very, very close to 3 without actually being 3. And when I do that, and I let this x become something very close to 3, you add 3 to it, it's something very close to what? 3 plus 3 would be 6, right? So we are saying that this is equal to 6 over, notice the limit's gone now, right? And now I'm letting 3 go here, right? 2 times 3, or 2 times something really close to 3 would be really close to 6, and then we add 3 to it, be really close to 9, so this is approaching 9. And then that's just what? 2/3. Right? That's it. Now, we're not saying that if you plug 3 into this function, it's going to spit out 2/3, right? We're saying if you graph this and you get close to 3 on the x-axis and look at the function should be getting really close. Both sides should be getting really close to the value of 2/3. All right. Next one. So this is the one you were going to ask about before, right? Okay, so on this one, I'm going to first evaluate. I'm going to plug 2 in, see what happens. Get 1/2 minus 1/2 over 2 minus 2, which is going to give me 0 over 0. So I have the form of 0 over 0, which means I need to do some algebra or some sort of trick. So the algebra I'm going to do here is, so what did you do? Whoever got this going here. You got a common denominator, so you combine these two fractions up here together. Any reason why? Yeah, I mean, that's what we did, right? If we have a complex fraction, we normally try and get reduce its complexity by bringing and combining fractions together. That's kind of what the trick is. Get a common denominator here, so I multiply the top and bottom of the first fraction here by 2. I multiply the top and bottom over here by x. That way I can put those two together. They'll both have the same denominator of 2x. And when I do that, I get 2 minus x over the common denominator, 2x over 2 minus x. And now what? Cancel the top and the bottom. So again, make sure you're very clear that the reason why you can cancel those is because you have a fraction over a fraction, like this. That's really the limit. X approaches 2. You don't have to show this. These are these little subtleties of algebra we have to be clear with. Division is same as multiplication of the reciprocal, right? So I'm flipping the bottom fraction up and I'm multiplying it, and that allows me to cancel out these factors. And now, at this point, I can do my replacement of x with 2. So 1 is all that's left on top. 2 times 2 would give me 1/4. I don't write the limit anymore, right? Because I've actually allowed x to become something very close to 2. So 1/4. Okay, let's take a poll. How many hundreds did we have? Oh, wait, sorry, I closed the poll. Try it again. How many hundreds did we have? All right. How many of you got half of the quiz right? Okay. I was hoping you'd say 100 on both, then I wouldn't have to grade them. All right, so the things I'll be looking for when I do grade them, of course, is the correct answer, but I'm also looking for notation. You know, correct notation. Did you carry your limit? You know, can I follow the work? Can you follow the work in 3 months when you need to go back and look at it? That sort of thing. Any other questions over homework? Or anything for that matter? I'm sorry? 23? So number 23 in the homework was limit x approaches 16 of 4 minus root x over 16x minus x squared. There we go. So let's first try and plug in 16. Get 4 minus root 16 over 16 times 16 minus 16 squared, which gives you what? 0 over 0. So I need to do some sort of algebra, some sort of trick. I see two potential things here. So I'm going to take any recommendations by someone who possibly got this. Maybe, what did you do? What? You factored an x out of the bottom? Okay. That's one way to approach it. Okay, after you factored out the x, what did you do? So did conjugate, okay? Conjugate? All right, for those of you who tried this, let's take a poll. How many of you did conjugate? Which means I'm going to multiply the top and bottom here by this. I'm not done. There, now I'm done. Right, I'm going to do conjugate, right? So a lot of you did conjugate. Did anybody realize that 16 minus x is the difference of squares? And do it as 4 plus root x, 4 minus root x? You could have done it that way too. You would have avoided the conjugate completely. Do y'all see that now? I mean, this right here is actually 4 plus root x, 4 minus root x as a difference of squares for this one right here. And then that, the 4 minus root x would have canceled right away. But that's not what I was told to do, so just pointing that out. Okay. Now, FOIL out the top, multiply out the top, right? Yes. So when I multiply out the top, now I'm going to rewrite this. Limit x approaches 16. What do you get there? 16 minus x. Things cancel out. You should get 16 minus x on top. On the bottom, we aren't going to do anything on the bottom. We're not going to touch any of that, right? We are going to just leave the x there. We're going to leave the 16 minus x there. And that 4 plus root x, we're going to just leave. Make sure we put it in parentheses, though. And is that good, or is that a good situation for us? Yes, because the factor on top, 16 minus x, cancels with the factor of 16 minus x on the bottom. I am left with a 1 on top, though. And now at this point, can I do direct replacement now? Yes. Now I'm out of room, so I'm going to just try and squeeze this in right up here. I'm going to put equal because I'm letting x go to 16 now. On top is 1. On bottom, I have this left corner here. This was x, so 16. And then the parentheses, 4 plus the square root of x. Square root of 16 is 4. So you get 1 over 16 times 8, right? 4 plus 4 is 8. 16 times 8. 1, oh, what is it? 128. Put it up there. 1 over 128. Okay. Any others? 27. Did anyone need me to leave that up there, or are we good? We're good? Okay. All right. 27, limit h goes to 0 of x plus h cubed minus x cubed all over h. So I first let h turn into a 0. If I do that, what would I get? X plus 0 cubed. What's x plus 0 cubed? It's just x cubed, isn't it? So I will get x cubed minus x cubed, which would be 0, and then divided by the h went to 0, so 0 over 0, so algebra time. Any suggestions here? Difference of cubes, I heard. Yes. Difference of cubes would mean you look at this as being something cubed minus something cubed. Is that what you mean? Then use the formula? Okay. Or what was another suggestion? Multiply this like x plus h times x plus h times x plus h 3 times. Okay. So let's see. How many of you would have wanted to do x plus h times x plus h times x plus h and multiply that all out? How many of you would have done that? Okay, I guess, yeah, that's, well, I think that is the method most of you wanted to go with, so I'll go with that, all right? So I have to actually figure out what's x plus h times x plus h times x plus h, which brings me to another question. We'll come back to this problem in a second. If I take x plus h and I raise it to the 0 power, what do I get? I get 1. If I take x plus h and I raise it to the first power, what do I get? Itself, right? X plus h. I'm doing this for a reason. Just hang in there with me. What's x plus h squared? So if you do the FOILing, all right, you actually do all the multiplication, you'll get x squared plus 2xh plus h squared. And then if you do x plus h cubed and multiply that all out, and I hope you understand what I mean is if you did this and maybe first started by putting those two together, which would have been this, and then coming through with this x plus h out here and multiplying it through, doing all that and then collecting all your like terms together, if you did that, you would get x cubed plus 3x squared h plus 3x h squared plus h cubed. That's what you would get if you did that multiplication. And there's a pattern here that's being created, and I want us to address this pattern because it's useful. It can be useful later. X plus h to the fourth would be, see if we can pick up this pattern. X to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. If you don't see the pattern yet, that's okay. I'm going to point the pattern out, but let me just do maybe one or two more of these. X plus h to the fifth. Okay, so I'll start pointing out the pattern first. Notice first the powers of x. What's happening to the powers of x as I move from left to right? They keep decreasing by 1. So my first term is going to be x to the fifth, plus I'm going to have a number here. Then I'm going to have x to the fourth, and then there's going to be something with h there. Plus I'm going to have another number, I'm not sure what it is yet. Then I'm going to have x to the third. Then I'm going to have some other number, and then I'm going to have x squared. Then I'm going to have another number. Then I'm going to have x. And then what about the last piece? X to the 0. So notice all the ones on the edge are just what? the h to whatever the power is, right? If it's 4, the last one's 4. If it's 3, it's 3. So this last one should be h to the, what, 5th? So as I move from left to right, the x powers go down. Or you could also say the h powers start going up. So like I don't have an h, and then I have a single h, right? So no h, h squared, h cubed, h to the 4th. So they're opposite, right? X's go up. I'm sorry. X's go down, h's come up. So I should have an h here, h squared, h cubed, h to the 4th, and then what? H to the 5th. And then the last thing to resolve is just what the numbers are. So those numbers come from something called Pascal's triangle. So I'm going to go back and I'm going to come in here with green. Hopefully you can tell that's green. I'm going to write the coefficients of all these variables. Coefficients are the numbers in front of them. Okay. Y'all see that? So let's take a look at this. On the edges, you always have what? 1s down the edges. So I know for sure this is going to be a 1. This over here in front of the h to the 5th is 1. So I know that. Now, let's look. The first row is 1. The second row, the 2 edges are 1s. The third row, the 2 edges are 1s, right? But the middle one is a 2. That 2 comes from adding the 2 numbers above it together. 1 plus 1 would have given us 2, right? Now look at, see this 3? This 3 comes from this 1 and this 2. This 3 comes from this 2 and this 1. Where does this 4 come from? The 1 and the 3. Where does this 6 come from? The 3 and the 3. Where does this 4 come from? The 3 and the 1. And then you always have 1s on the edges. So what should this number right here be? 5. And that came from here and here. This one should be 10. This one should be 10 again. This one should be 5. And you could keep going and doing this over and over. Okay? The numbers, if you just put the numbers without all the letters, just the number, it's called Pascal's triangle. It was named after a mathematician, Pascal. But he didn't create it. The Chinese created it many years before he did. But for some reason, he gets credit for it. So this is a good way to like show off to your friends, I guess. Because you could keep going, right? Don't tell them it's Pascal's triangle. Just tell them you know how to expand this in your head. So what would the next one be? What's the next one? X to the 6th plus 6x to the 5th h plus 15 x to the 4th h squared. Next one, 20 x third h to the 3rd plus 15 x squared h to the 4th plus 6, we're almost there, x h to the 5th plus h to the 6th. So that's what the expansion would be. It's better than having to multiply that together, right? Okay, last thing I want to point out, last thing, is that if you focus all your attention right now on just the first 2 terms, okay, just the first 2. The first one, of course, is always x to the 6th, right? The next term will always have that same 6 is going to be right here, right? The power on the x came down by 1, the h went up. Let's see, these 2 terms right here, same pattern, right? You have x plus h to the 5th, that means x to the 5th, then here's your 5, right? The power of 5, and then with the power on x came down 1 and the h is there. This is going to come into play later on because I'm going to refer back and I'm going to remember we did Pascal's triangle? Remember those first 2 terms had that pattern? It's going to help us do something. All right? So some of you, I think, may know that I use Mathematica to do all my stuff, and I asked you about Wolfram Alpha. Yes, Wolfram Alpha. Wolfram Alpha is this website. You can go do all this math. The brains behind Wolfram Alpha come from this program. Okay, this Mathematica is a program that is put out by the same company, Wolfram. So I'm going to write some code real quick, just to show you how advanced mathematics is. I want to expand. Oops, I got to spell it right first. I want to expand x plus h expand means multiply it out, raised to the n power. And I would like to let my n start at 0 and end at, let's say, how many powers do I want to go up here? We only went, what, 6? I'll go to 200. I'm missing something. Too many brackets. So I'm running the code right now. All right. Try to make this a little bit bigger for you. So with that simple code I just wrote right there, right now this is x plus h to the 0 power, which we said was what? 1? What's x plus h to the first power? X plus h, right? What's x plus h squared? Now it's the order's backwards. Don't worry about that. That's x squared plus 2x plus, right? That's cube, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. 13th. I can just drag this. That's pretty cool, right? So it just shows you, I mean, do you really need to know how to expand something by hand? I mean, these days, I mean, you don't. It's an algebraic skill, though. We need it in calculus. But we're getting to that point where, like, technology is, we got to, at some point, bring this into the classroom. We're not there yet. But it would be nice if everyone came in here, they all had their own tablets. We could all just bring up Mathematica. We could expand polynomials, do a bunch of other stuff. Let the computer do the hard work. Let's do some more fun stuff with it. But we're not there. All right. Any other questions? Oh, wait. Sorry. Oops. Should go back here. All right. So what was x plus h to the third? It was x cubed plus 3x squared h plus 3xh squared plus h cubed. That's just the expansion of x plus h cubed. I still have next to it what? Minus x cubed, and then all of this over h. And something good is about to happen. X cubes cancel. And now notice that every term that remains has an h in it. And if you recall from last time, what we said is when we were doing limits, we wanted the bad thing to cancel, right? And the bad thing for us is the h. So when we look at the numerator, I pull the h out. I pull a single factor of h out of every term on top. I know some people like to say, like, can't I just cancel the h? And I'll say yes, but this is what's happening. We're pulling an h out. We're canceling it. And now your problem should be gone. You can let h go to 0. So if I let h go to 0, does it have any effect on this? No. How about this one? Yes, it kills off the 3x completely, and then this one is gone. So all that remains is what? 3x squared. Okay. Anything else? Did anybody do number 28? I did 28 in class? No? You did? Did it work out? You think you got it? Yeah, that sounds right. Good. Okay, let's move on with today's material, okay? Here we go. We are still in 1.4. We were calculating limits. We had all the limit laws. And I started to do these problems from the book, right? Then there were the two, continuing in the notes, there's the two important limits that were on your quiz that I'd say maybe 5 or 6 people got correct, maybe more. So I put in here, you know, two very important limits, and I think in my video I was like, you need to know these, and you know, so these are the ones I was talking about. And then I was going to do some examples here. These two limits that we need to know, you cannot show algebraically why they are what they are. Okay? Cannot be shown algebraically. So let me convince you of that. If I say, what's the limit as x goes to 0, sine of x over x, you know sine of 0 on top is 0. So you know that this has the form 0 over 0, yes? But how can you do anything? I mean, the answer should be 1. According to what I'm saying here in the notes, the answer for this should be 1. Do you realize you can't do anything to that? How are you going to factor this? Or break it down algebraically? You going to cancel these? Hope not. What would that be if you did that? That's what it would be, right there, a sin. Right? That's not my joke, obviously. Someone else came up with that. It's not funny, but any humor we can find in a course like this, right? Any humor we can find, we'll go with. So we can't. So someone is just going to tell us that this is true, all right? And we're going to believe it for right now. Then later on in the course, we're actually going to show why it's true. We're not there yet. So taking this on faith that this is equal to 1, and then the other one, which I won't write up here, we're set off to do a bunch of examples. But I'm going to add a little bit of a twist to this, because even though that's the formula that would appear in the book, I want you to consider this in a different light. If you have the limit, and it will not matter what's happening down here, okay? So I'm leaving them as boxes. I'm saying you have a limit. It could be anything going to anything. It doesn't matter, okay? It doesn't matter what's going on here. And on the top, you have sine. And then up here, I'm going to use a different color. You've got something up here, which I like to call junk. That's inside your sine. And then on the bottom, you have the same exact junk. I mean, even though that's just some junk and this is still some junk, it's the exact identical junk. Same thing, right? The answer to this limit will always be 1 if these two conditions are met. Okay, this will be equal to 1 if, first of all, we'll say A, the junk matches. That's what I just said. It has to be the same top bottom, right? The junk matches. And the second thing, the junk goes to 0. It means when you take the limit, that junk is going to 0. If that happens, if those two things hold up, the answer is 1. If one of those two don't match, you can't do it. So let me show you how this will work. Oh, one more thing. I'll do this one in blue. If you swap it up and you put junk on top and you put sine junk on the bottom, the answer will also be 1 as long as those two conditions are held. So for this one, it doesn't matter if the sine's on top with the junk inside and the junk's on the bottom, or if it's the other way, junk's on the top and the sine of the junk's on the bottom. Either way, as long as the junk's going to 0, as long as the junk matches, you're in business. Your answer is 1. So let's take a look. First example here, let's find the limit as x approaches 3 of sine of x minus 3 over x squared minus 9. It's the sine function. Welcome back from pre-cal. So tell me what's happening. Do what we normally did. Plug 0 in. Plug 0 in. Plug 3 in. See what happens. On the top, we get sine of 0, right? Over on the bottom, what do we get? 0. Sine of 0 is 0, so this is the form 0, 0. So according to our cheat sheet thingy, we're supposed to do some algebra or some sort of trick, right? But the algebra that we're going to be able to do is weird because we've got a sign in here and we're not quite sure how to deal with that. We haven't really had to up to this point. So do you see that we have something inside of the sign which we could look at as being our junk? Does this junk go to 0? If I let x go to 3, does that junk go to 0? Yes. Okay, how about down here? Does this go to 0? Yes, but do they match? They don't match. So you can't use that yet. You can make them look, you can make a match though by doing the following. You recognize the denominator as being what? Difference of squares. So you factor it to be x plus 3, x minus 3. Yes? And now let me rewrite this limit in a different way. And you tell me whether or not you agree or disagree that this is the same exact problem. Is that the same thing? I'm just using properties of fractions in multiplication, right? If I take a fraction times another fraction, I just go straight across with multiplication. 1 times this is this. X plus 3 times x minus 3 is this. But by peeling it apart like this, I can now use the limit laws. The limit laws tell me I can do these two things separately. I can take the limit on each one. So what would happen if you take the limit here? Well, x minus 3 goes to 0. X minus 3 goes to 0. They're identical. They match, right? X minus 3, x minus 3. In this case that they both go to 0 and they match, this entire thing is going to go to what? 1. Now plug 3 into this one, and what do you get? 1 over 6. So this one goes to 1, so I'm going to put equals 1 times, this one is 1/6, so your answer is 1/6. 1/6. Let's take a quick vote, see how you felt about that. Now, graphically, again, what we've said is, basically what we're doing here is we're taking a function and we're looking at its graph, right? There's my graph. This is the graph of, let me see how I can, I don't want to leave that, never mind. This is the graph right here of sine of x minus 3 over x squared minus 9. That's the graph. At 3, right, at 3, it's undefined. But if I go up here, what should my value be? Getting close to. Wow, I look way off. 1 divided by 6, right? What's 1/6? 0.16 something, right? And look over here on our y-axis. What is it? 0.16, somewhere around there. Understand? See the connection between the graph and our limit. So without the graph, we were able to figure out how that function was behaving. But we had to rely on that little junk thing going to 1. Any questions? Shall we try another? Sure, okay. Sounds great. Let's try this. Limit, let's go t goes to 0, sine of 4t over tangent of pi t. So our rule of thumb has been for all limits, always just try and plug in the value, right? Let t here become 0. If you let t go to 0, you get sine of 0 on top divided by tangent of 0. Sine of 0 is 0. Tangent of 0 is also 0. So we have the form 0 over 0. So we have to do some sort of algebra, some sort of trick, something. So this is one of those problems where, I'm going to show you this first time through, and you're going to go, okay, yeah, maybe I would have never thought to do that, but now I've seen you do that, so now I know maybe I should try that next time when I am faced with something like this. So what I like to do is this. I like to identify what's causing the problem. So the division by 0. So I like to peel this thing apart like this. Okay, is that the same expression? Yes? All right. What's causing me trouble is the tangent pi t, right? Because that's going to 0. It's causing division by 0. All right. 1 over tangent, right? That's the reciprocal of tangent. Let me try and get things in terms of sine and cosine. That's cosine. 1 over tangent is cosine over sine, right? Because this is cotangent. So could I rewrite it like this? Limit t goes to 0, sine of 4t over 1 times, what did you say it was? Cosine t, it's cosine, not t, cosine pi t over what? Sine pi t. So could I do it this way? I could, right? I mean, you might be going like, why are you doing all that? Like, I mean, just leave it all together. Cosine pi t over sine pi t, if I put those together, that would be cotangent pi t. Cotangent pi t is 1 over tangent pi t. So what I've done is I've converted my tangent in terms of sine and cosine, and I've peeled everything apart. I've peeled it all apart so I can identify the part that's causing me the problem. Right? That's the part that's causing the problem. This is giving me division by 0. When I plug t as 0 into this, I get 1 over 0 undefined. This is all okay, right? What's sine of 0? 0. 0 over 1, 0. What's cosine of 0? 1. What's 1 over 1? 1. These two are fine. The last one's the one that's causing the problem, right? So this is where we have to cook something up, all right? Take our vote real quick and make sure everyone's comfortable up to this point while I go to the next step. Remember what I said, though. What I'm doing here does not necessarily, if it's the first time you've ever seen it, doesn't seem natural. Like you wouldn't just automatically start doing this, right? I can't see that percentage over there. All right. Looks like we're up over 80. Does anyone have a question? We're not done, right? I mean, just getting, yes. Pi times 0 is 0, right? Pi times 0 is 0. Cosine of 0 is 1. And that's either off your unit circle or your graph of sine, however, or cosine, however you're comfortable with that. Okay. Any others? Any other questions? All right, so here's where the magic starts to happen, all right? Watch this. What would I love to have up here? What? Close? All I heard was pi. Pi t. Why? Why would it be nice to have pi t right here? Because I would have junk up here, junk in here, they'd both go to 0, that would turn into 1, wouldn't it? If I had pi t. So I'm going to force pi t to be there. And to force it, what I mean is I have to come in here and arbitrarily introduce a 1 to the problem. And the one I'm going to choose is pi t over, I only have one option, pi t. Right? That's all I can do. Now I'm going to, on the next line, I'm taking this pretty slow. So what did I do there? I mean, I had to I rewrote the whole thing. My hand hurts now, but I rewrote it to help you see that all we do now is what? Take that pi t, it's all multiplication, just slide it on top of that sine pi t, right? And now I have the format I want. This junk matches this junk, right? And according to what I had said before, right here, that if the junk is on top and the sign of junk is on the bottom, it's still going to go to 1 so long as they match and they both go to 0. So you agree that we're good here? That this is going to go to 1? Okay, so let's go back through this. This goes to what? When we let t go to 0, this one goes to 0. This one goes to 1. This one goes to 1. This one, that one, that one is undefined. So it's like a person in a boat and they plug up one hole and another hole pops up, and that's what we've done. We fixed one problem, we created a new one, didn't we? But now I'm going to be very, very clever because this is all multiplication. I'm going to take that t, which is causing me the problem, right? And because it's multiplication, I'm going to slide it all the way down here, and I'm going to put it underneath this sign for t. And the only thing I'd be missing now is a what to make this thing become something nice. A 4, right? Do y'all see that? I'm going to take this t here, slide it under here, and then I just need a 4 down here to make this sine 4t over 4t go to a 1. So how do I introduce a 4 on the bottom here? I have to put one up here and one down here. So let me rewrite the whole thing now. Here's what I have. Limit t goes to 0. I've got the 4 over 4, but I'm going to write it as 4 over 1 times sine 4t over what? 4t. And then times cosine pi t over 1 times pi t over sine pi t times what was still over here? 1 over pi, right? Yes. I could have, but then the junk wouldn't have matched. It would have been 4t and then pi t. And so even though they both go to 0, they don't look identical. So I don't want the pi there, so I just left it behind. I said, fine, you just stay there at the end. I'll bring in the t here. I'll introduce my own 4 to make it match, but I have to do it on the bottom and the top. You sure? We got to make sure. Let's take a vote because My expectation here is I'm going to lose. I lost a lot of people. This is not a. It's not a very natural thing. It's probably first time you've ever seen this. It's like, what the hell are you doing, man? Okay, so let's talk about this. Where can I clarify? I'm sorry. What about the cosine? No. Nope. So cosine of pi t over pi t, as t goes to 0, is not 1. It only works for sine junk over junk or junk over sine junk. Yeah, if we go back to the notes, we have a slightly different one for cosine. It's cosine x minus 1 over x, and that one goes to 0, not 1. I need to stop turning and looking at the board. I'm giving myself a headache every day when I do that. I'm used to being in a classroom where I'm standing more like to the side, so I'm like, you know what I'm saying? Like I can see you and like this, and this is just. Okay, come on. What else can I clarify here? Come on. I'm going to leave this poll open. As you understand, click yes. We need to get that to 80. If you don't ask a question, I can't help you. So you have to tell me where in this you're confused or what part of it is troubling. Okay, is it why I did it or is it how am I doing it algebraically? Why? Okay. Okay, when I had put this pi t in here to make this division by 0 go away, right? I introduced the pi t to make this thing become a 1 instead of division by 0. But when I did that, I had this new pi t down here. Now that went to 0. See, in this line, when I let t go to 0, I get pi times 0, which is 0. 1 divided by 0 is undefined. So now I'm like, shit, that t is causing a problem. I need to somehow get rid of that problem. And then I say, oh, shit, look, there's a sine 4t down there. You don't have to say shit. That just kind of helps you a little bit sometimes. You say, look, there's a sine 4t way down there that I can use this t underneath it to create that 1 that happens in the limit. But I've got to move it all the way from there down here, which I am allowed to do because it's all multiplication, right? This is 1 times, well, I should go back up. This is 1 times sine pi t times pi t. So move things around with multiplication. Just slide it all the way to the end, drop it under this one. So now you've got a t down there, right? You got a t down there, but you don't have 4t, which is what you need. So you make the 4t appear. The good news about making the 4 appear is that you don't introduce a new t. You just introduced 4 and 4. Over here, we had to introduce the pi t. Same thing without the t, just the 4. As long as it's 1, as long as it's a 1. 4 over 4 is 1, though. Right? That's the key to it. I'm not changing the problem. Everything I put into this problem is a 1. It's just a clever one that makes things work the way I want them to work. Yes? Pi t over pi t is a 1. Right? Pi t over pi t is a 1. 4 over 4 is a 1. So I technically have not changed the structure of this expression. It's identical to what it started. It just looks different. Which makes you think, well, if you could do that, then you could go change anything. You can, but it's not changed. It's the same number. I mean, it's the same expression. It's equivalent. Without this little magic of making things appear and sliding them around, you would not be able to evaluate what this thing is doing. And that's part of what makes this little part of this section a little challenging, because it's not like the limits that we've been doing where it's like, hey, I know I'm going to have to do difference of squares, or maybe I'm going to have to factor, or maybe I'm going to see conjugate. This one is like, you've got to cook this up yourself. You've got to make it happen. Okay, we're still at 68%. Are we not going to be able to break 80 on this one? It's okay if we can't, you know. I mean, I think for a problem like this, if I can get, that's close enough, but I'm still open to questions. All right, if we vote and I still have, 85, 95%, and you're in that 5% that's still confused, This is your education. You can stop me or you cannot stop me. It's on you, right? Oh, we're gonna do a couple more. Yeah. Yep. We're not done though, right? We still have to figure out what happens here. So let's finish this one up. We have, let's just look at these all individually, all right? I'm looking at this as 1, 2, 3, 4, 5 separate factors. And I'm going to see what happens as I let t go to 0 on each one. I'm going to actually let t go to 0, so no more limit. 4 over 4 is, 4 over 4. 4 over 1 is 4, times sine junk over junk, the junk matches, 1, times cosine 0, which is 1 over 1, 1 times junk over sine junk, junk goes to 0, 1, times 1 over pi, which is 1 over pi. The answer is what? 4 over pi. Now, let me give you a warning, okay? In a problem like this, which might appear on a quiz or a test, you might notice that in the very beginning of the problem, our final answer turned out to be 4 over pi, right? If on a quiz or a test, you don't show any of this stuff, and you just put 4 over pi, you're not going to get any credit, all right? You got to go through this, all right? I hate grading these problems because I have to see all the detail, but it's the way it is. And another thing is they don't always work out that way too, so you have to be real careful. How about this one? Limit x goes to 0. Cosine x minus cosine x sorry, make that first one squared. There we go. I just made up this problem. I'm not pulling it from the book, so let's see what happens here. Cosine squared x minus cosine x over sine x. What happens as x goes to 0? What's cosine of 0? 1, 1 squared, minus 1, 1 minus 1, 0, over 0. 0 over 0 is a bad thing, so now we need to do something. Now, I should be thinking that this is probably a junk problem because I've got sine in there, right? Let me remind you of the other formula. We do have one for cosine, okay? The one for cosine works the exact same way as the sine one does, except that, well, I'm saying you can replace the junk, okay? So the one for cosine says cosine junk minus 1 over junk, okay? That one's going to go where? To 0, not 1, all right? 0. You remember on the sine one you could flip it over? You cannot flip this one over. Why? Well, the sine one you can flip over because if it turns out to be 1, then flipping 1 over is still 1. If this one turns out to be 0, then if you flip that over, you get division by 0 is undefined. So it doesn't flip. Let's see if we can work through this one with that. Anybody have an idea what we could do here? Take a cosine out. Limit x goes to 0. Let's see, factor cosine out. And what do we have now? That's what you wanted me to do? You lead me the rest of the way until I feel like I need to lead you the rest of the way. So you want to start peeling things apart now? So you can identify where the problem is? So you're saying take it out as a 1 over sine x like this. Then what do you want me to write? You want me to do cosine x over 1? You want me to do that? Over 1. That would be excellent. I like that idea. Now let's just make sure everyone else is okay with that. This is multiplication. This is cosine times this in parentheses. That's the same as this. And then the single sign on the bottom I can write as 1 over sine x here. Okay, quick vote. Are we okay with that peeling apart? And now, you see where the problem is, right? This sine x. So you're going to fix it by doing what? Putting an x on top, which means you have to put an x on the bottom. I'm with you. I know a few of you have this already. You're going to put x over x here. And then you're going to take that x on the top and slide it where? Top of the sign. That will fix that problem, won't it? It'll fix the problem of that division by 0 here. But it created a new problem of having the x on the bottom here. But you're going to fix that by doing what? Moving it under the cosine x minus 1, because then it would match that formula right there. That one worked out real nice. So here's where we are. We have x over sine x times cosine x over 1 times cosine x minus 1 over x. I believe at this point, everything is going to do something I can handle. All three factors are going to behave in a way that I'm okay with. X over sine x goes where? 1. Cosine of 0 is 1 over 1 is 1. And then cosine x minus 1 over x is 0. The answer is 0. The limit is 0. Okay, let's try one more. What's the limit? I forgot to ask you if you're okay with that. You can tell me now. We might do 2 more. This one might be a little too basic. Where's the problem occurring here? The bottom, the division by 0, right? How can I fix the division by 0? X over x? If this were an x squared, I'd have 1 there, wouldn't I? So I'm going to have to come in here with x over x. Okay, let me rewrite the problem real quick. Limit x goes to 0, get sine x squared over, what should I write here? X squared, and then what's still out here? X over 1. Now look at these individually. Do you have any issues now? What's this one go to? 1. What's this one go to? 0. 0 divided by 1 is 0, and that's just 0, and that's fine. So you're going to get that this equals 1 times 0, which is 0. All right, the last one I'm going to show you is part of your homework problems, but I very rarely get a student who gets this one. So I think it's better just to show you because, again, it introduces a technique that you may not naturally use. Now we're using theta instead of x, but theta is just a variable, so it may as well be x. The biggest issue in this problem is that plus sign. Because you have a plus sign in the denominator, you cannot start peeling things apart like we did before. We forgot to check. Is it 0 over 0? Yes. 0 over theta is 0, so 0 plus tangent of 0 is 0, so 0. It's all 0. We're good. 0 over 0. Right? So, without me dragging this out any further, let me show you the move, unless somebody sees it. No? Theta plus 2. So like creating like a squared thing? Man, it might, but I'm going to put here what I'm going to do, and then I want you to look at it and tell me why I'm going to do this. See if you can think through this. I'm multiplying by 1, right? Here's the original fraction, right here. I'm multiplying it by 1, but I chose my 1 to be 1 over theta times over 1 over theta. What will happen when I multiply this 1 over theta times this? It'll be sine theta over theta, which is sine junk over junk. It'll turn into 1, right? Yes. What about here? I don't have to distribute the 1 over theta to both of these? Yes? What's 1 over theta times theta? 1. What's 1 over theta times tangent theta? Well, that's going to give me tangent theta over theta, isn't it? Yes? But what's tangent theta? Sine theta over cosine. So I'll have a sine theta on top, won't I? And I'll have a theta on the bottom? And won't that give me a sine theta over theta is 1? So I'm saying this hoping you kind of see it. I'm going to show it, but trying to show you where the instinct to come in with that came from. So let me distribute through. I'm keeping the limit because I'm not letting theta go to 0. Passing this through, I get sine theta over theta. I'm not turning it into a 1. Why? Not yet. Why? I haven't taken the limit yet, right? Okay. I'm passing the 1 over theta to here and here. So my first one, I get theta over theta. That's going to turn into a 1. Turn into exactly 1. I mean, that just simplifies, right? Theta divided by theta is 1. So that's going to turn to 1. The next one was, what do we say? Tangent theta over theta? Do you mind if I write it this way? Tell me if this is not still tangent theta over theta. Is that? What's the sine theta on top over the cosine theta here? Tangent theta, and then there's your theta on the bottom. Isn't that the same exact expression? Saying, isn't this that? So now take your limit and tell me where everything goes. And we said that the bottom left corner was a 1. So sine theta over theta goes to 1 over the bottom left corner is 1 plus, what was this sine theta over theta? 1 times, what's 1 over cosine of 0? That's going to be 1. So what's the answer? 1/2. I'm real curious to see the vote on this one. The voting is not would you have done this? The voting is, do you see what I did? And do you understand the algebra of what I did? Yes. What's cosine? I'm letting theta go 0. What cosine of 0 is 1. 1 divided by 1 is 1. You just have to go back and look at your trig stuff. Make sure you're comfortable with all the values of sine and cosine. All right, so you should be able to handle, well, I'm not going to say you should be able to handle. You should at least have a launching point to get into page 45. You should do 49 through 55 odd. 49 through 55 odd. And you can try the evens. I did some of them already. All right, for homework. I'll write it down. I am page 45. It'll be 49 through 55 odds. And try the evens if you'd like. What did I give you for homework last time? Was it 11 through 27 odd? Did I say you should try the evens there also? You should try the evens. I mean, there's no such thing as doing too many problems in a class like this. All right. It's kind of funny. I've gone back and I've looked at when I was in calculus. I wasn't the best student until about Cal 2 is when it all kind of came together for me. And what I started doing in Cal 2 that was different was I started doing all the problems. So like I tried to just do every problem out of the book. And when I got to the ones that were more complicated in the back, I just kind of nah. But like the ones towards the front near the homework section that I was given, I sat there and I tried doing them. And then I went and I found that folder or the binder I used years ago, and I looked at it, and like I would say 80% of what I did was wrong. But I was trying to do it, and I was trying to do it before class. I was trying to do it before lecture. So I was trying to read the book, and I was trying to do the problems on my own. That's the change that I made for myself when I started to get serious about doing better in my math. Tried to get ahead of the class. And then when I get to class, I'd realize I did a bunch of stuff wrong, but now I was familiar with the wording and everything. So do more than you're asked. It'll benefit you. Okay, we have like only 13 minutes or so. We are going the next section that we're supposed to cover. Where's my folder? There it is. Today was supposed to be finishing up 1.4, I believe. Yep. It says on the calendar we're supposed to do 1.5, then 1.6. We're supposed to have an exam a week from this upcoming Tuesday. So we have this upcoming Tuesday. A week from then is our first exam. I plan on covering 1.6, then 1.5. So I'm going to go reverse order. Do the 1.6 first, then 1.5, even though on the calendar it says 1.5, then 1.6. So what I recommend you do is that you also watch the course video for 1.6. Right? Course videos for 1.6. Watch that before class on Tuesday. We're gonna start talking about this concept of limits at infinity. So what we haven't done yet, every time we've taken a limit, we've always said, let's let x go to 0, or let's let x go to 3, or x go to 2. How about letting x become infinite? So look at your handout, the cheat sheet I just gave you right now. Okay? I want you to look at 1, 2, 3, 4. The fourth one down on the left side there, where it says fixed number over infinity. We'll talk about this on Tuesday. I'm going to let you go, don't worry, but I just want us to start thinking about this. What happens to a fraction anytime your numerator is headed towards a fixed number and the denominator gets huge? It gets smaller, right? It gets smaller and smaller and smaller. We are going to need that in this class. We're going to need to know this. Know that when that happens, our answer is 0. There's no way around it. Okay, there's no algebra that needs to be done. But then look at the last one on this. Let me give you an example next to this one so you can see what I'm talking about. If I say limit x, I'm going to use this notation right now. X goes to infinity of 10 over x. What's happening here is my numerator is what? Fixed. It's 10. The denominator is headed to where? X is headed to infinity. It's getting huge. Anytime that happens, fixed over infinity, the answer is 0. There's no work to do here. Right? No work. But then take a look at something like this. What's the answer? It's not 1. Okay? Now, someone's going to do that on a test. Because as soon as they see sine x over x, they're going to be like, oh, junk, man, this is 1. It's all good to go. Right? That's what's going to happen, I promise. What's the issue here? Junk's not going to 0, right? You got to have the junk match. You got to have it going to 0. Here, it's going where? Infinity. But the numerator, the sine function, is what we consider to be a bounded function. Think about sine. What is it doing? It's oscillating up and down. It's always between two things, right? 1, -1, 1, -1, 1, -1. But the denominator of this thing is getting huge. So it looks like this. I'm going to graph it. Sine x over x, right? Come on. Oh, I forgot the division there. Oops. There we go. So there's your sine function, right? It's trying to be a sine function, but as it's going out, it's getting smaller, right? Because the denominator is getting huge. Let me go further out. I'm just making it fancy now. There it is. So if I zoom in on it, you can kind of see what's happening. You know, our values, they're oscillating back and forth. Look at right here, 0.1, right? Negative 0.1. But as I start going out real far on the x-axis, right, it's still oscillating, but look at how small these values are. Look at way out here. I mean, you're talking about 0.001. And if I keep going further out, these will get even smaller and smaller and smaller. So it's like a funnel effect. That function is starting to get closer and closer to 0. So that's why that last one says anytime you have bounded over infinity, it's going to 0. Nothing you need to do. But you need to be able to recognize you have a bounded function on top. I think we're done, right? Anybody have any comments or concerns? Do your homework. 1-6, watch the video. Start studying. Start going and looking at your homeworks so you can be ready for this test.